Hey, welcome. Anybody have any questions from yesterday? No? Okay, so we'll just go through some stuff. We'll just work it out together. Okay, so the first thing, let's just go through the Schrödinger cat case to start with. This should be easy. All right, so I covered that in class. So this is just a good warm-up. The circuit, as you might recall, were 2 qubits. Right, so this was the undecayed nucleus. And then here, at this point, so then we'll work out what takes place here. So first of all, so we should find out that we have an entanglement between the state of the cat and the state of the nucleus. So let's just go through the first part. So what we have is 0 equals the undecayed nucleus. 1 is equal to the decayed nucleus, right? So this is undecayed nucleus. This is the decayed nucleus. So let's go through it. So the Hadamard transformation, H of 0 equals, anybody know the answer? 0 plus 1. Which is pictorially, it's the undecayed nucleus plus, I'll just add some dots there. Okay, so you have that. Then let's go through to calculate the C0 operation. So this is the cat is alive. So a living cat. And then here we have the cat qubit. 0 is at the ears. So it's the living cat. And 1 is equal to the dead cat. Okay, so there's a dead cat. And then let's go through the controlled knot operation. So we have C0 acting on. At this place, we have the first qubit is 0 plus 1 over root 2. Here. And the second qubit is 1. So what's the next step? Sorry, based on the control bit.
After we do our tensor product.
Yeah.
Based on the control bit, this is the first bit
Yeah. Okay, but the first step, you're right. You're doing a couple things at once. First thing is just linearity. So this is equal to C0, and then it's 1 over root 2, 0, 0, plus 1 over root 2, C0, 1, 0, right? Okay, now you can go ahead. Now based on the control bit. So what's the first term? What? Okay, good. Yeah. And then the next one? Okay, so that's just 0, 0 plus 1, 1 over root 2. And so that's the entangled state. Entangled nuclear cat state. So that's the easiest way to do that problem. Any questions about that? Clear? Okay, good. Okay, so that was just a starter. Warm us up. Then the next one I wanted to do was the case of Hadamard acting on all qubits. So let's just take the case, let's see that H tensor n on the state 0 to the n. See that? Okay. Yields a superposition of all numbers from 0 to 2 to the n minus 1 for just the case n equals 3. So we'll just do the case n equals 3 and solve it. Okay. So let's begin with just n equals 1. And we see that h from the previous board, h of 0 is 0 plus 1, which is root 2, which is correct, right? That's equal to 0 plus 2 to the 1 minus 1. So that's correct for as well. Okay, let's do n equals 2. And we get h tensor 2 on 0, 2. And so in this case, h tensor 2 on 0, 2, let me explain. This is the same as writing, h tensor h acting on 0 tensor 0. Okay, stop me if it's not clear. So this is notation. H tensor 8 is 0 cross 0. And then here we use the bilinearity property. So this is equal to h on 0 h on 0. Okay? Then this is equal to 0 plus 1 over root 2. 0 plus 1 over root 2, which is equal to, sometimes when I do this, the cross symbol is optional. So sometimes I write it, sometimes I don't. I don't if I think it's obvious. It should go there. So this is 0, 0, right, the first term. Second term, 1, 0 plus 1, 1 over 2. And then that's equal to, I could just put it in one cat. So I get 0, 0 plus 0, 1 plus 1, 0 plus 1, 1 over 2. And then I just rewrite it in base 10. So we'll do base 2 to base 10. And then in that case, from base 2 to base 10, we know that, so if I do base 2, base 10, 0, 0 is 0. 0, 1 is 1. 1, 0 is 2. 1, 1 is 3. Do you know what I'm doing? Okay, anybody have any question on that? Okay, so then we just write this in base 10 as 0. And then I'll just put a subscript on to indicate it's base 10. Plus 1 in base 10. Plus 2 in base 10. Plus 3 in base 10. Over 2. And that number is the same as 2 to the 2 minus 1. So that's proven. And then we'll just go through the n equals 3 to make sure you're clear. And then I'll do the n equals 3 case, building on this, so the general proof would be by induction. So we'll just do H tensor 3 acting on 0, 3 is just equal to H, which way should I do it? Left. I'll do H tensor 2, 0, 2, which we've just done, with H on 0. Right? So this case we did here, and this case we did here. So it's equal to, and then I'll just go back to the base 2. So I get 0, 0 plus 0, 1 plus 1, 0 plus 1, 1 over 2. And here I'll get 0 plus 1 over 2. And then we just multiply it through. So we get here 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, plus, yep, right, 0, 0, 1, good.
0, 1, 1.
Yep.
0, 1.
Good.
1, 1.
Right. And this is all over. Sorry. My fault. Yeah. And then when you reorder this, this is equal to 0, 0, 0. Okay. And then we'll go over base 2 to base 10. And then we get and that number is 2 to 3 minus 1 over 2 root 2, and it's correct. And then if we went to the proof for all n proceeds by induction. You guys know what induction is? Okay. All right. So this is the first step in the Shor algorithm that prepares superposition of all numbers. I mentioned to you that, just note here, that H tensor n on 0 n is, I'll just put it in quotes, it's quantum parallelism. So that's the quantum version where we prepare a superposition of all input states. Okay, so far so good? Next problem? Okay, so the next one, just want to go through the exponentiation. So let's figure out how to make a qubit gate. So That was number 2, yeah, I'm missing 3. Oh, no, I see. Okay, number 3 is to generate a single qubit gate from a single qubit Hamiltonian over time t. So the purpose of this problem is to help you be able to connect the Hamiltonian to the unitary map. So we'll write down what the Hamiltonian is for a single qubit. Single qubit Hamiltonian. H equals, and then I'll just write that it's AX plus BY plus CZ, where A, B, C are all real numbers. And let's make sure that we understand how to write that in the matrix. So this is equal to A, 0, 1, 1, 0, plus B, 0 minus I, okay, and C, great, which we can write in a single matrix as, so C, what should I write here? Okay. Yeah. C, okay. So, thank you. Okay, so that's the general form of the single qubit Hamiltonian. And then the gate it generates. So the gate is U equals e to the minus IHT, which is equal to e to the minus I. C, A minus IB, A plus IB minus C times T. Okay, how should we expand it? So we're going to use a formula. There's a couple of good ones. How should we do it? So what's your favorite formula for an exponential? Cosine sign won't actually help because then you have a cosine of the matrix, which thing's correct, but it won't help us. If anybody wants to run down and do it, it's fine too. What? Can't hear you. Baker Campbell Hausdorff? Is that what you said? It's easier. What? Taylor, okay, so that's one way. So one way, we could use e to the a equals
1 plus
yeah, sum I, well, wait, n, k is 0 to infinity. What would I write? Minus I, a, oh, sorry, I don't need that, minus a power n. Yeah, that's one way. Or what's the other one? 1 plus k? I don't understand. 1 plus a?
Yes. Plus a squared by 2.
Aren't you just doing that?
Oh,
No, I think you're repeating this one, right?
the other way is BCH.
No, it's easier. The other one is, do you know, okay, so with your exponential formula, you know, if you write e to the x, there's like a 1 plus,
X squared divided by 2.
no, you're doing that one again. So we already wrote that.
1 minus x. 1
Okay.
over 1.
Do you know this one?
The power series.
No. 1 plus x over n, limit, we take the limit as n goes to infinity. Sort of, yeah. What? No, you guys don't know this one? This is, should have learned it when you were children. No? All right, make it visible. It should be in your head. E to the x is the limit. N goes to infinity. 1 plus x over n to the n. Visible? Does that ring a bell? Okay, so we can use the same formula over there. That's another one to use. To me, this is the definition. So when I think of how to define an exponential, if I do proofs, I start off there, and the Taylor expansion becomes a calculated result. So you have to define your exponential. So there's a couple of choices, right? So here we could have the same thing. We would just have something like the limit n goes to infinity, 1 plus a over n to the n, something like that. Okay, since you're all familiar with the Taylor expansion version, well, let's work with that one, I guess. So here, okay, so if we do the expansion, we need to do the square of the matrix and the and cube and so on. So what's the square? Let's just call this, that's h. So what is h squared? It's equal to c, a plus ib, a minus ib minus c times itself. If anybody, there's shortcuts to do this. So if anybody sees the easy way, say so. Otherwise, I'll do the slow brute force method. First entry. Sorry. Plus or minus? Plus a minus b? Is that right? I'm just your secretary. Okay, what's the next one? Sorry. AC. That's it? Minus AC. Is that right?
Yes, sir.
Okay, next one.
AC
AC.
plus iota BC.
Yeah, I know when you, what you mean, okay.
Minus AC minus iota BC.
Okay. Next one.
A square plus B square.
Okay. Now let's simplify that. What? Delta t, is that what you said?
A square plus B square is minus.
Inside or outside?
You can write outside. A square plus B square plus C square. And identity. 1001. Yeah.
For this defined to be. Okay. So then what's h cubed?
H square H.
Yeah. Okay. H squared h, not tensor.
A square plus B square plus C square identity into H.
So we do a squared plus b squared plus c squared, identity, times h. So we get rid of the identity, h. So we have a periodic property. Okay. So what's the exponential? So now plug it into here. This goes to the cosine sine business now. So we have e to the minus iht equals, so the first term is an identity. The second term is minus iht. The third term is, what should I do?
I square is minus.
Change that to minus? I'll write,
and t squared.
I'll just write that for the moment.
Yeah.
Okay. Next term?
And divided by 3t.
H cube.
Okay. And then so on. So we'll just go to there and check it, and then that's equal to. So if we group the even terms, so let's group the even terms, we get identity minus half h squared t squared, and so on. These are even powers. And then over here we have minus I h t, identity, minus 1 over 3 factorial. What? X squared? What? X? H.
H squared.
E squared. And these are odd powers. Is that okay? Okay, so let's simplify. So it's identity minus, and what's h squared?
These are all odd powers.
H square plus b square plus c square divided.
But yeah, we also have to worry about t squared. And then that's just the identity again, and so on. Minus IHT, identity, minus, and then here h squared is going to be no, h is out there.
Nick, another H squared.
No.
H cube.
Lost. H squared. Okay. So what's the final result? Do you know it, or do we need to do more terms?
Cos A square plus B square plus C square into
So it's cos this? No?
simple T.
What? This?
Yeah.
Okay.
Minus iota sign. Into that one.
Okay. Sorry. Sorry, there's no half here. Wait a minute, let's go back. How do we get this? Is that right? Yeah, okay. Sine of, is that right? Okay, good. Is that not right?
I have objections.
Objection. And noted. Your objection is sustained.
Yes.
Yeah.
The first, the second step, you have written over there odd powers, they are not odd powers. 1 plus 1 minus 1 by 3 that will be h square.
H is common. H is common.
H is okay. If h is common, if you separate h, then you can't write the even powers in terms of sign. If we include h in all powers, then we can write the sign.
Sine is for odd powers.
Yes.
So h times here. So this times identity is odd power of h. H times this is h cubed.
Okay.
So it's an odd power.
Yes. Fine, but in the lower step, minus iota sign, h cannot multiply.
You mean this is wrong?
Yes, yes. This is included in sign already.
No?
Yes.
Okay. So we disagree. Anybody want to weigh in? Yeah.
So, the thing is, I feel like
Sorry, are you addressing his problem or are you raising a new issue? No, let's sort this one out first. I said, let's weigh in. So he's saying this is wrong. Is it wrong? Okay. So let's discuss. Yeah, but that's not a discussion. You can't just say I'm right and he's wrong. We have to go through why. Okay, so let's go through and expand what you're saying. Okay, how do you want to resolve it? You're saying what I wrote is wrong. So what is the correct answer? How do we do it? You want to do it? Sure. You changed to a plus. You sure you want to do that? No, are you sure? You also changed my minus to a plus.
Oh, sorry. So H is included. These are our powers now.
Included. What? I can't hear what you're saying. What does included mean? There's nothing in here. It's empty.
So the same thing.
But, okay, so it's not that you're not disagreeing, but when I do this,
I have objection.
I have another objection. So h squared is something times identity, right? I'm putting a constant inside. Why do you want an operator inside?
So this H is also operator inside.
I know, but you just wrote the second line with nothing in it. It didn't help me. So we need to get the h outside. So the problem is, do you agree? Okay, h squared is a constant times the identity.
Yes.
Agree? So the nice thing is I have a power series without an operator. You're insisting on making one with a power. So once you put the operator in the sign, what are you going to do? You have to do another Taylor expansion.
H squared is identity.
H squared is a constant times identity.
That is what is missing. He's saying that H is inside science.
Are you telling me or him? Okay. Okay, but we need to sort it out. Does he believe you? You're not saying anything wrong, but you're saying that mine is not right. Both are correct, but then I'm claiming mine is useful. Okay, so I admire your courage to come up and do it, but let's go through here. Can you simplify that expression? So I wrote from here to here. Do you follow that step?
No, because how to write this expression in terms of sign?
Okay,
This is
what's
my-
h squared? What is h squared?
Yes.
Okay, so I write it in there. Then I have an H matrix on the outside, and I replace that with a constant times identity.
Okay.
And then that allows me to simplify in this way. So in my case, the H comes out, and then I just have an identity matrix on the inside with a constant.
But the okay, this one is- you write-
Anybody else wants to run up, you can go up.
So the sign expression you can write it like this. But here is h squared, and then you will have h4.
H squared की value डालो ना उसमें. H squared की value डालो. हर जगह H squared की value डालो. H4 is H squared into H squared.
And what about t squared?
T squared will remain there. It's T cube. It's not T squared.
T
Okay. I got it.
Good.
If you have operator in exponential, then you can write it as exponential e for iota theta is cos plus iota sin theta. This is correct only when you have a constant in exponent. But if you have an operator, then you can write it like
Hmm.
this.
Okay, we agree.
Then I might be an identity n dot sigma 2 by 2 matrix.
That formula is used for poly matrices.
Yes.
Poly.
So, no, 2 by 2. So the following formula is correct only when you have an operator in exponent. But this formula is true when you don't have an operator, only a constant. So I was thinking to apply this formula.
Yeah,
So this formula.
great. We agree. We agree. That's perfect. You can keep teaching.
So yes, you agree.
You agree.
Do you have any further
Okay.
objection?
Good job. Okay, that's great. So then what's nice is that from here, we get the result that if we have a Hamiltonian generated unitary, it's just the sum of an identity with another operator. So it's easy mathematically. And then we do this for all orders. If you take 2 qubits or 3 qubits, so with 1 qubit, we find that, where'd it go? It's all lost. What? Yeah, but there must be an answer here somewhere. Third last line. Yeah, here. Okay. So we have the identity minus an h, and then it's a power expansion of this type, but it truncates at second order because the square is a multiple of identity. If you had 2 qubits, then the fourth power is a multiple of identity. So the one easy way to go from a Hamiltonian to a unitary operator is to do the power expansion, and there's always a finite order. There's always some finite number where it's a multiple of identity. So that's how you can convert a Hamiltonian to a unitary. Next problem, ready? Any questions on that? Good discussion. Thanks for coming up. Okay, next one. Let's take the Heisenberg model. So we had the Heisenberg model. And this one we have a Hamiltonian is a sum. I told you the notation is not very good, not clear. So that's why it's good to go through it. I is 0. Let's say k is 0 to n minus 1. Identity, just think sigma. I plus 1, I minus 1. Okay. Actually, let me put it up on top. Identity, tensor product. So that was for one dimension. So what we have, let me explain each thing. So this is equivalent to writing, for this one we have x, so it's x for the kth cubit. I'll draw a picture. X k plus 1 plus y k plus 1 plus z k plus 1. Subscript, there's no subscript. Superscript. None of them are visible? Not that much. Okay, let me try again. Let's see. So this is k plus 1. I can't hear you. I can't hear you. Can you speak up?
The first identity, shouldn't it be K?
Oh, k.
Starts from 0. K starts from 0.
Yeah, k starts from 0.
Shift from 0 minus 1.
No, I'll explain. What you're worried about is how can you have a negative 1? I'm saying it's not a good note. I'm just going to go through and explain it, but I don't like the notation. This is what people write in physics papers. So this is x. The superscripts are visible now, right? So it's x k plus 1 plus y k plus 1 plus z k plus 1. Okay, then we can have the rule that the identity, so if I do an identity with a negative 1 up here, well, identity tensor some number, so some number less than or equal to 0 vanishes. So if that number is 0 or negative, then we don't write it. That's what I'm saying is the notation. And then the same kind of rule here. This one is vanishes if that's going to, if n minus 1 minus k is less than or equal to 0. So then we have a rule about vanishing. And then what we've got is, we're imagining is a system like this. So we have one dimension, and then we have some set. So these are qubits. And then we have, this will be k. This will be k minus 1, k plus 1, k plus 2, and so on. So then what we do, let's work out what that matrix is, make sure we understand it. Okay, so what we're doing here is we're just summing. It's the pairwise interaction, first pair, second pair, third pair. So it's what we're doing is taking, so on that line, we take an interaction here. There's an interaction here, interaction, interaction. So these are interactions. And then we add them up. That's the concept. So let's go through to understand xk plus 1. So let's do xk plus 1. So let's understand what that means. This is x on the first one. And then this is x on the next one. So it's a tensor product, outer product. And then this is equal to, I think I did it in class. So it's 0. Yeah, thank you. Okay, so that's what this means here, the first part of this, but it's sandwiched between identities on the left and right. And I'll go through it carefully again. And then we take our yk, equals. So in this case, what should I write? Can you see the answer immediately? Instead of 1, I'll have a minus I or an I. So say 0, 0, minus I. Next row. Is that right?
0 minus iota 0 0.
0. You said minus?
Plus iota 0.
Okay, does everybody think that's right?
It should be minus 1.
Yeah, so you don't think it's right. Okay? So what do you think I should do?
I makes 1 and minus 1.
You're not speaking in full sentences, so I can't figure out what you're saying.
1 minus 1.
What is 1 minus 1? That's not a full sentence. We have to speak in sentences or I won't understand. Has to be a subject, a verb, an object.
I will replace by 1.
I will be replaced. So you're saying replace I by 1. All the I's by 1. Is that correct now? Looks like we have to do it the slow way. Is he right? Even more wrong. Okay. Let's go through it slowly. Zero. Okay. Equals 0 times all that. Minus I times all that. 0 minus 1? Minus 1?
No, sir, plus 1.
I'm only a secretary. So if he says minus 1, I write minus 1. You want me to change it?
Yes.
Okay. Next one.
0 1
0,
0.
1, 0, 0.
Minus 1 0 0 0.
Okay. Is that self-adjoint? If we take the transpose of the complex conjugate,
Yes,
Yeah.
sir.
okay. So that's a good sign. Okay. And then let's do the last one. Can we do this in our heads? Do it in our heads or do it writing? Should we go through the slower way? Do it what? Slowly. Okay, so it's 1, 0, 0, minus 1. Outer product, 1, 0, 0, minus 1. Equals, what? 1, 0, yeah. Okay? So we've done it. Now we have to add them together. So let's do the next step. Okay, so the next step is, let's do our sigma k dot sigma k plus 1. Okay, can we add them in our head? So I'll just write a big matrix. Sorry, 1, 1, 0, 0, 0. Let's make sure we agree. We don't agree.
1 minus alpha.
Change this.
Oh, sir.
There's no
There's no what?
Okay.
We do? The last one's 0? So you added this matrix to get a cancellation. Okay. Good. This is a democracy. We're gonna, majority wins.
0 minus 1,
0.
2, and 0.
What?
I'm getting
2,
and 0.
0. Next one. Okay. And that's the one I had in my slide, if you have the slides. Okay. So yesterday I just put it up there as the answer, but now you're able to derive it. Okay. So this represents the case of, that would be 2 coupled qubits. Now we have to exponentiate that in this case. So let's go through and now calculate. So let's calculate the gate. Gate for 2 Heisenberg coupled qubits over time t. How do we do it? I can't hear you.
I can't see.
Okay, I'll write bigger if you talk bigger.
Sure.
Okay. Okay. So I just said here, calculate the gate. Calculate. So this is problem 4, I think. I didn't. 4. Calculate the gate for 2 coupled qubits, 2 Heisenberg coupled qubits over time t. Okay, so how should we do it? What should we do as the first step? Give you a hint. We're going to do the e to the minus I sigma dot sigma, and I'll call that 1 qubit, 2 qubit over time t. Okay, so what did we do before? We did a power expansion. We squared the matrix. So we square the matrix. So if we'll do sigma k dot sigma k plus 1 squared. Can we do it in our heads, or shall we go slowly again? Slowly.
You get it from this, right?
I didn't square it in the slide. What? Yeah, PowerPoint had that, but I didn't square it. Yeah, okay. So, slowly, okay. Should I write the matrix twice? I mean, no, okay. So you can see, what's the first entry? Okay. 0? Remember, I'm a secretary now. I'm only going to write what you tell me. Next? 0? 0. Next row. 0? Is that what you said? Sorry, I don't hear what I'm supposed to write. 0. Next. 1? Okay. 4? 5? 5?
It's got to be 5 instead of 1. The second.
Change this to 5?
Yeah.
Next? Minus 4? Okay, next row? 0? Minus what? Minus 4? 0? Okay, does that look right? Okay. Well, it's not a multiple of identity, is it? So shall we keep going? Okay, so let's do sigma k dot sigma k plus 1 cubed. Now I didn't check it. Is that correct? You sure?
Yeah, that's
Seems correct means is correct. Correct? Perhaps. Okay. You're hedging your bets. Okay. What's this equal to? So we can. So let's agree. We can take this times this or this times this. But you can say. Okay. So what's going to be? Tell me what to fill in. First entry. 1. 1. Next. 0. 0. 0. Next row. Help. Come on, you're doing this. What? 0. There's a lot of brains in this room. Minus 13. Next. Come on, you guys. You got to be faster. We won't get. I got more problems to cover. It's arithmetic. What's this mean? 14. Next. 0. Okay. Okay, so now let's do the next one. It's got to end sometime, I promised you, remember? Sigma k dot one zero. You guys are getting good at that. Nice to hear. Next row. Here? 4. Oh, yeah, okay. 41. Minus 40? Is
Yes, in fact, it's 25 minus
that what you said?
9.
What? 9?
I don't know.
Minus 40 and 41?
41.
Is that right? Did it really switch to positives? Yeah, it was negatives in the diagonal, positives, negative, positive. Yeah, it seems right. Four. How many powers do we have to go? Are we getting it right?
Yes.
Why do I think it should have stopped by now? Okay, so let's just double check. So when you did it, how were you doing that? Were you multiplying this times the cube in your head? Or were you doing the square of that?
Square of
Okay, you're doing square of this. Okay, so it was square of this was 25 and 16 is 41, yeah. All right. Let's see. So it's the power of 4. No, that's bad. If we square that, what do we get? Let's just check here. Make sure it's going to end. Okay, so I'm going to skip some steps. At some point, it's got to stop. So if I do sigma k plus 1 to the power of 8, what do we get? So 40 squared, just to be sure, 40 squared, 1600. 41 squared is, what? 1681? Okay. Yeah, it's going to keep repeating, isn't it? All right, I'm not sure why. Why is it not periodic? Sigma. Something's bugging me about this. Got to be the cross terms, because if we do square of this, yeah, the square of this works. The square works, and we get the cross terms. Okay, maybe it doesn't converge. Maybe I broke my promise. So I'll think about it later. But that makes it hard to solve, because we have to do the Taylor expansion. That's annoying. All right, let's go through and figure it out. Okay, so basically what we're winding up with is the power series. So we'll get that when we do the e to the minus I, and then we do sigma dot, so sigma 1 dot sigma 2, t, and we get the sum minus I, n factorial, let's see, minus I, and then we have that matrix here, t, well, t to the k, kth power, minus I to the k factorial, and this is what we've been working out. That matrix is just the powers of this. So if we don't get convergence, it would have to go on forever. All right, and everybody checked all the calculations. All right, I'll work it out later, figure out what's going on. Let's hope to get a closed form matrix.
It doesn't convert if that's the right.
Yeah, you check it. Yeah. All right. Okay, so that's what we have to calculate. I mean, that's what we do. Yeah, maybe that's right. Okay, so that anyway, that shows you how to Okay, that shows the first one, the Heisenberg matrix for two coupled qubits. And then I'm going to put in, I want to keep that term. So let's do the next problem. Just finish writing. Okay, the next one was 3 qubits. So I'll finish here. So this is the calculation to obtain the unitary map for the 2 qubit Hamiltonian according to Heisenberg model. Okay, so we didn't get a closed form solution, but that's the way to do the calculation. And then why it didn't close, I need to think about it. Okay, let's go to I'll just do the 3 qubit case so you're clear. So we'll do the 3 qubit, 3 coupled qubits in a one-dimensional line according to Heisenberg according to the Heisenberg model. And that one I'll just write it down according to our Hamiltonian is it's equal to identity cross sigma 1 dot sigma 2 plus, so it's, I'll just do it here. So it's these two coupled and then those two coupled. Oh, so I shouldn't do it that one. It should be sigma 0. So I'm labeling them 0, 1, and 2. Sigma 0, sigma 1 cross identity plus identity cross sigma 1 dot sigma 2. And then let's figure out what it is. So in this case, we write the matrix, which we have here. It's 1 minus 1. 1. Yeah, 0, 0, 0. And then it's, let's see it, 0, minus 1, 2, 0. 0, 2, minus 1, 0. And here, and we multiply that by the identity, and we add the identity outer product with the same matrix. Okay. Can we do that in our heads or slowly again? So let's do the first one, and then we'll add to the second. What? Sorry, I heard 101? 1, 0. Yeah, 1. Oh, sorry. Okay, start me off. Are you going down or across? Okay, 1. So I can't follow anything. 1, 0. Okay. What's next? Here, beside or block? Okay. Next. Okay. Next block. I don't know where to write them. Down 0.
4 zeros. No.
Okay, let's say you got 0, yeah, 4 zeros in a block. Next.
Minus 1, 0, minus 1.
Okay,
Minus 0, 0,
2, 0, 0, 2.
0, 0, 0, 0.
Okay, good.
0, 0, 0.
2 zeros?
2, 0, 0.
Okay. Okay, plus, this one's a bit easier. 1 block. Well, this is easy, right? Just write the whole block. Okay, so that's the first block, right? Second one is going to be all zeros. Next one is all, yeah. Yeah, whole block. Okay. And then finish it with this. Two, yeah, just do one row, not blocks. 2, you said? 2, 0, 0, 0. 7 zeros, yeah. Okay.
0, 0, 2, 0.
Sorry? Yeah, right. 0, 2. Is that right? Yeah, okay. All zeros? Fourth through?
4 zeros, then 4 row. Now you are in 5th row.
Okay. All zeros? You're saying make that a 0? Okay, what do you guys think?
4 zeros, then 2, 3 zeros.
Sorry, 4 zeros, then 3 zeros.
Then 2, then 3 zeros. 2 and 0 square.
Oh, you mean swap these?
In the bottom.
Huh? That's what he's telling me.
Previous hours.
5 zeros, 2 zeros.
Okay, that's what I had before.
Yes.
You agree? Okay, next.
0, 0, 2.
0, 0, 2.
Start. 0, 0, 2.
0, 0, 2.
0 minus 2.
What?
0, 0, all zeros.
You guys agree?
No, that cancels out that one.
Next.
0, 0, 0, 2.
0, 0, 0, 2.
0 minus 2.
0 minus 2,
2, 0.
2, 0. Next.
0, 0, 0.
0, 0, 0. All zeros?
4 zeros. 5 zeros actually. 5 zeros.
2 minus 0, 0. Not minus 1.
Next
0,
row?
0, 0, 0, 2. Last one.
Last
one.
and then
The last one is 2.
Think that's right? Okay, check. Is it Hermitian? If you take the transpose, do you get the same matrix? Is that right? We've got 3 non-zero elements here. 3 there. Okay. 2 minus 2, yeah. And then this is what I gave you in class, remember? I don't know if you have the slides. Do you have the slides? They don't have a... What? Yeah, okay. So I'm just checking. Minus 2, 2 zeros, right? Yeah, okay, looks Good. Yep. That's what I gave in class. Remember I gave these Heisenberg matrices? So now we've derived 2 out of the 3 that I had in the slide. So when you get the slides, you'll see it. How are we doing for time? 10 minutes left. Okay, I think let's do a graph. We'll finish with a graph. Okay, so the final question is, final problem, number 6, is to express H equals sigma 0, sigma 1 identity plus identity sigma 1, sigma 2. I'll make sure I got it right. Sigma 1 dot sigma 2 as a graph. So in that case, we're going to label the rows and columns. So I'm going to label it by 0, 1, 2, 3, 4, 5, 6, 7, because when I do quantum information, I like to include the 0. So that's the column label. These are the row labels, 0, 1, 2, 3, 4, 5, 6, 7. Okay, so these are column labels. And these are row labels. Then, how should we do it? Going to make a graph. So we'll pick a row. Let's pick the 0th row. So I'll make a vertex for number 0. And then I make an edge. So where do we see what non-zero entries are in the 0 row? Sorry?
0 column.
So,
Non-zero entry of 0.
yeah, so that's a self-interaction term. You're right. That'd basically make a loop of size 2. Next one. That's it. Okay? There's no edge, just a loop. Then let's take number 1, first row. So where's the first non-zero entry? Third column. Second? Third column,
Third column, but there's
0.
just 2, right?
Second column. So it goes to number 2. And it's got a weight of 2. And this is the first, we're going to color the graph. So it's the first non-zero entry. And when we look back, we double check. So if we go to the second row, and we look for that, which numbered entry is it? So you see, this was the first non-zero entry of row 1. Now, and that's column 2. Now we look at row 2, and we look, where is the corresponding one? Well, that's here. It's the first one. Do you see? So I put a number 1 here to indicate that if that were the row, then this is the first non-zero column entry as well. So I have.
Sorry, I lost you.
You lost me. I'm sorry?
Can you
Okay.
do that again?
Okay. So we took this. This is the first row. Then we put a 1 there because the first non-zero entry is the value 2 in column 2. Now we flip it around. It's a Hermitian matrix. So now we say, if this 2 were the row, this entry is in the first such column, second. Yeah. So this is in the first column. Okay. So now we go to the second row, row number 2, and we've already done this. Now we draw an edge for the second non-zero column entry. So number 2 is where?
Number 2.
Number 2 is number 2? So you're saying that's self. So I'll put a loop on. Okay. Where's the next one?
There's another 4.
4. So we go to number 4
The weight of 2.
with a weight of 2. Okay. Now let's go to row 4. Where's the corresponding one here? What?
I'm not getting how to make the graph out of that matrix.
That's what we're doing.
I'm not getting it.
But, okay. Do you want to go to the beginning?
Yes.
It's okay. Okay. So let's go back to the beginning. And so what we're doing is to create an efficient representation of the graph to save space and time on the computer. And it'll be a quantum computer. So we don't want to keep track of the zeros. So let's go to the 0th column, and then we say we only want to keep track of the non-zero entries. So the 0th row has only one non-zero entry of value 2 in the diagonal element. So we just went here, I wrote the number 0 inside of a circle, and then I did a self loop. So the self loop keeps track of the diagonal entry. So I looped it back to itself, wrote the number 2, and that represents this. And there's no edges coming out, so it tells me that there's no non-zero entries other than the diagonal. So far, so good? Okay. Now we go to row 1. So remember, the row 1 is here. So then we ask the question, and we go in the obvious order, where is the first non-zero entry? The first non-zero entry is in column 2. It's the only non-zero entry. So then I say, I draw an edge to column 2. Got it? So this is the first row. There's a non-zero entry in the second column. So I put the number 2 for the second column here, and I draw an edge. The edge tells me that there's a non-zero entry in row 1, column 2. See? So that's what that tells me. It tells me that's the first one, and it tells me that the weight of that entry is the number 2. But, as I said in class yesterday, the matrix is symmetric. You transpose it, you get itself. So row 1, column 2, there has to be the same entry in row 2, column 1. So we go to row 2, column 1, we correctly see the 2, and we see that it's the first of 3 non-zero entries. So I put the number 1 to let you know to let us know that it's the first one. Does that make sense there? Everybody get it? Okay. But row 2 has 3 non-zero entries. So I want to know what the second and third non-zero entries are. So the second non-zero entry, one's a diagonal, I don't care. So I don't need that. 1 was the diagonal, so I made a loop with the value -2. So that loop tells me the diagonal entry. Then we go to the next one, and that's in column 4. So I write the number 4 here,
Yes.
and I put the value. Clear? Okay. But now, let's go backwards. So we wrote the number 4. Now we go down to the 4th row. So we have 0, 1, 2, 3, 4th row.
This is one non-zero entry.
Yeah, so it's only got a...
This is
Let's go back to 2 and put the weight of 2.
This is
Fifth row, it's fifth.
0, 1, 2, 3, 4.
Non-zero and that entry is fifth non-zero entry. Yes, sir.
Only one non.
Yeah, that's correct. Why are we debating it? You're right. Yeah, okay. I'm satisfied. So we go back here, and we see that it's got a non-zero entry in 2, which is correct. And then we know the weight is 2, which is correct. And there's only 1. So we don't need a number at all, but I will number it. I'll just put a number 1 to say that. And then that's it. And we keep going.
Why did you put a 1 there?
Because eventually I want to color the graph. So there's only one possibility. But later when we color the graph, then we look at the pair of numbers. So if this is a 1, 1, we color it. So we might make that red if it's 1, 1. We make it blue if it's 1, 2. So it's just by keeping track, that ordering will give us a coloring. I told you about the graph coloring problem. Okay, we're almost out of time. So let me just do another step and then we'll quit. So 1, 2, 4. Let's just go to 3. So 0, 1, 2, 3 has all non-zero except column 5. So we have the number 3, we have the number 5, we have an edge between them, 2. Value of the edge is 2. And it's the first one for 3. Which one is it for 5? So now we go down to 0, 1, 2, 3, 4, 5. And then we see 3. Okay, so it's number 3. And then with 5, we'll also have 0, 1, 2, 3, 4, 5. We get 0, 1, 2, 3, 4, 5. We get a self loop and one other edge. And the one other edge goes back to 3, right? Yeah. So we have a self loop of -2. Now what's going on here is you get the idea. So we're constructing the graph that represents that matrix, and then what happens when we do it is we have to decompose. So basically, when we take our Hamiltonian, in this case, we have more than one non-zero entry in each row or column. We write it as a sum of Hamiltonians that have only one non-zero entry per row or column, and I didn't tell you how to do it, but at the compiler stage in the quantum computer, this graph coloring goes on, and then it creates gates to be able to execute in the quantum computer. And I just don't have the time to teach all of that. Okay, but you get the idea? That's how you construct the graph?
Yes.
Okay. So these are, what I'm really doing in going through all this is I'm just giving you bits and pieces so you understand some aspects of the quantum compiler steps without covering everything. It's just a flavor of it. So we'll break.